When we talk about reaction mechanisms, we'll often kind of talk about an intermediate or a product or a starting material, and we'll talk about the stability of that compound. Unfortunately, in chemistry, stability doesn't mean just one thing, and so we need to talk about what we mean by that term. Right? So stability can be kind of one of two things. We could be talking about kinetic stability, which just means that the compound doesn't react quickly, right? Does not react quickly. If you're speaking to an organic chemist says stability, usually this is what an organic chemist means by stability. Although there are exceptions to that, as always, they could mean thermodynamic stability. So thermodynamic stability, which we've also, if you've taken organic 1 or organic 2 from me, we've talked about thermodynamic stability as well, right? Thermodynamic stability means that a compound is lower energy, right? It's favored as product in an organic reaction, in reactions. So when we talk about thermodynamic stability, this kind of takes us back to general chemistry. We can look at reactions and say, is this product favorable or is the starting material more favorable? And we had a mathematical equation that we could figure this out, right? If we find the delta G naught of that, that can equal delta H naught minus T delta S naught. Are you guys having flashbacks to general chemistry at this point? Right? This is the free energy of reaction. If this number is less than 0, that means that we have a favorable reaction. Right? The reaction will proceed to products. This is thermodynamic stability. Right? And so we can talk about things like delta G and all of that kind of stuff, but usually when we talk about these things, we're going to talk about it graphically. And so we can graph energy, we can graph delta G or energy on our y-axis, and then on our x-axis we can have basically the progress of the reaction. If I start with my starting material here and I go to my product here, I can graph how does that energy change. If my starting material has some value, I'm going to choose just kind of an arbitrary value for that. I'm going to say that my starting material has a free energy value of about here. And if my product is more stable, more thermodynamically stable than my starting material, then my product will be lower on that graph than that, right? So in this case, we would say that our product has greater thermodynamic stability. I gotta get used to writing with my pen again. Right. In this case, the product has greater thermodynamic stability than the starting materials. Right. However, the pathway in a reaction from the starting material to the product is not a straight line. Right? This depends on the mechanism, and this is what we're going to be talking about in this course, is how do we identify what kinds of things happen along the way between starting material and product. Right? Furthermore, it's not just a straight line from here, right, to here. If that were true, then we'd never have any starting material, right? Because the starting material would immediately convert to product and you wouldn't be able to isolate that starting material as it occurs there. Instead, we have these steps in our mechanism, and every step has a barrier. So we're going to draw another one of these that's a little bit larger. And in this case, I'm going to have my starting material in the middle, and I'm going to have two possible products. Product 1, product 2. You can probably see where this is going. Right? Here's my delta G on my y-axis, etc. My starting material is some level of stability, let's say here. And then I have two possible products. So product 2 is going to be more stable than my starting material. Product 1 is also going to be more stable than my starting material, but it's also more stable than product 2. Okay. As I move from starting material to product 1, right, we have to go through a barrier to get to that place. So this mechanism, this is a one-step mechanism. Right? So starting material to product 1 is a one-step mechanism, a concerted process, meaning it only has one transition state, right? It goes through one transition state. This very top of our hill here is our transition state. We can measure how high that transition state is on our diagram. If we go from here to here, this value is the difference in delta G. So delta delta G, we don't write delta delta G, we write delta G double dagger. This is the activation barrier. This is how much energy it takes for this reaction to start, right? In order to get this reaction to produce product 1, we have to put in enough energy that our starting material can get over this activation barrier. Once it gets to that level, it gets to the transition state, everything after the transition state is more stable than the transition state, and so it falls very quickly to the product. Okay. We could draw another route, right, that has a much smaller activation energy, right? In this case, from here up to the top of our hill, here's another delta G double dagger, right? This would be delta G dagger number 2, dagger number 1, right? Another activation barrier. You can see that delta G dagger number 2 is a much smaller value than delta G dagger number 1, and this means that this is the more kinetically favored product, right? So when we're measuring whether a starting material is kinetically stable, we're looking at these delta G dagger values, right? How high is the barrier of reaction? The lower that delta G double dagger is, lower delta G double dagger equals lower kinetic stability. So we've seen examples of this. We have lots of examples of kinetic control versus thermodynamic control, right? Starting material to product 2 would be the kinetically favored product, right? It has the lower kinetic stability, and so it'll favor the formation of the product there. So we could look at something like the formation of an enolate. Right? If we have a primary alpha carbon on one side and a tertiary alpha carbon on the other, treat this with a strong base, low temperature, this will give you the kinetically favored product. Whoops, points off for me, there we go. Right, this will give you the kinetic product, what we call the kinetic enolate, right? This progresses through the lower delta G double dagger activation barrier. And the reason is because LDA is a very large base. It has a lot of steric repulsion. And so when that steric repulsion of those large bulky groups of LDA interact with our tertiary carbon over here, right, that creates a much higher energy, a much more strained transition state. Trying to bring two very large groups into the same space is going to create instability. That instability is reflected by the higher activation barrier here. It's much harder to bring LDA into contact with a tertiary carbon than it is to bring it into contact with a primary carbon, right? And so the activation barrier is much smaller, and we get the kinetic enolate. We remove the hydrogen from the less substituted carbon because the transition state is much lower energy. Transition state has less steric repulsion and is lower energy. Right? We control this by not putting very much heat into the reaction. We run this at very low temperatures, so we limit the amount of energy that's available. We don't have enough energy to get over this higher activation barrier. On the other hand, of course, if we add some heat to this, use a less sterically hindered base, like sodium hydroxide, a much smaller base, right? Sodium hydroxide isn't going to create as energetic of a transition state if it interacts with the tertiary carbon because it's not as large. So we reduce that activation barrier. We add enough energy now that choosing from one or the other is instead going to be determined by the stability of the products that we form. Right? And so in this case, we end up forming the thermodynamic enolate because this thermodynamic enolate has the lower delta G naught. Right? This is the more stable alkene because it's more substituted. This is more thermodynamically stable. It's less reactive. And so that's the thing that will form. If we have enough energy to get over both transition states, we'll always end up forming the more thermodynamically stable compound. So this is the difference. We've seen this example before, but now we have the kind of the reaction coordinate diagrams to match with that. One more thing to say about reaction coordinate diagrams is that we can also have multi-step mechanisms represented here. So in the example before, we used a single-step mechanism, but we could also have something like taking an acid chloride and doing hydrolysis of that acid chloride. Right? If I add NaOH to that, you guys all remember your organic 2. NaOH is going to add to that carbonyl, push electrons to the oxygen, and we're going to end up with an intermediate that looks like this. And then we're going to lose Cl minus to get ourselves to the carboxylic acid. Right? So same deal. We had our delta G here. Right? We start with our starting material on the left. We're going to our product on the right. Only this time we have an intermediate, right? It's not a single step mechanism. So we're going to have to stop at this intermediate somewhere along the way. So an acid chloride and a carboxylic acid are pretty close in energy. I would say the carboxylic acid is a little bit more stable. So we'll have that thermodynamic stability reflected there. The intermediate being charged, right, is much less stable. We have a neutral starting material, a neutral product. The intermediate has this charge on it. It's clearly less stable, and so we're going to push that up here a little bit. Right? Now, we have to travel from starting material to intermediate to product. We know that each step is going to have an activation barrier, right? And so now we look at what's the relative activation barriers of these, which of these steps going from acid chloride to intermediate or going from intermediate to product is going to have the greater activation barrier. Well, getting the NaOH to add to the acid chloride is actually the slower step, the kinetically less favored step, so we're going to give that one a bigger activation barrier. Once you make this intermediate, losing the chlorine leaving group is actually very easy because chlorine is a good leaving group, right? Plus you're neutralizing this compound to make a neutral carboxylic acid as it goes. So now we have our intermediate is here, but now we've created 2 transition states as well, right? So we have a transition state for this first step. As the NaOH approaches the carbonyl, we create a transition state. This has an activation barrier, right? Going from starting material up to transition state, this is our delta G double dagger for that step. It's a pretty big one, right? Then we have the activation barrier going from the intermediate to the product, right? A much smaller number here. So you can see, obviously, the second step is a much more favored process. Once you get that NaOH to add to the acid chloride, you're pretty much home free, because that second step, by definition, you're going to have enough energy around to make that reaction happen. So we can represent transition states and intermediates. So when we draw our mechanism now, right, NaOH has this negative charge, adds to the carbonyl, pushes up on the oxygen. What we're seeing is, right, we're kind of mapping that on our reaction coordinate diagram. As this comes in, right, we're bringing this negative charge in here, we're creating negative charge that's creating this kind of unstable compound. We get to the intermediate, much less not as thermodynamically stable because it's higher energy, but also not as kinetically stable because the activation barrier is all of a sudden much lower. And so very quickly, we're going to see that the loss of the chlorine is going to result in the final product. And so we'll be talking when we get to more complex mechanisms, we'll be talking about intermediates and stability and things that are favored and all of that stuff. And so the language that we're using there is grounded in these reaction coordinate diagrams. So now we've seen some of this, right? We know what is represented at each position here, right? Where intermediates are, transition states, all that kind of stuff. So we'll use that going forward.